Yeah, so we can start directly. This is section 3, called First Steps in Representation Theory. So in the book, this is about chapters 5 and 7. Well, so recall there is one important example of a Lie algebra, namely GLN F, where F is a field, N is an integer. So this is the set of n by n matrices with coefficients in the field, and the bracket operation is given by xy minus yx, where this is the usual matrix multiplication, the implied product here. Or I'm not sure whether I already introduced this notation, so maybe this is a definition here. If I write V for the vector space f to the n, I also use the notation GLV for the same Lie algebra. So this is a more invariant notation, and if I want to use an invariant definition also, which is does not depend on a basis of V, so this is the set of all linear maps from V to V, of course, with the same definition of the bracket. We even saw in the exercises one example where this V was infinite dimensional space. So this was a Lie algebra of operators. But anyway, so it's all the same thing, just here we think of linear maps as matrices. Here we think of them invariantly. So this is one basic example of a Lie algebra, and the idea of representation theory is the following. These Lie algebras of type GLN F and their subalgebras. So we've seen such also. For example, this O3 was a subalgebra of GL3. So matrix Lie algebras and their subalgebras are the concrete or manageable ones. So these are just matrices, so we can calculate with those, and it's something very concrete. We can write elements down, as opposed to general or abstract ones. According to the definition, a Lie algebra is just a vector space with a bilinear map satisfying some properties. So this is a rather abstract notion, and it's not clear at the moment from the beginning how would we start to think about those. It's just this map, and this is somehow the idea. The good Lie algebras are the sub-Lie algebras of some GLNF, And so the go, how do I want to put it? Oh, well, this is the idea. So we start to think for the moment about these subalgebras of GLN F. So for the time being, we fix L in GL V. So I use this invariant notation now, just GL of a vector space, sub-Lie algebra, or Lie subalgebra. So one thing, one advantage of talking with these concrete matrix Lie algebras is that, well, we have matrices, we have vectors here in the vector space, so we can do linear algebra. And the most important linear algebra concept here is the concept of an eigenvector and eigenvalue. So first thing is to think about eigenvectors and values. Yeah. And this gives the rise to the definition of a weight vector here. So fix a vector v in V, which is supposed to be not the zero vector. And this is by definition a weight vector. For L, so for this the algebra in GLV, we fixed if the following condition holds. So whenever I pick an element of the Lie algebra, so this is a subset of the endomorphisms of this vector space, and I want V to be an eigenvector of X. So X V, this is matrix vector multiplication, and this should be given by lambda V for some lambda, for some scalar. So this this is the formal definition, and informally one states this usually V is a simultaneous eigenvector. For and it's somehow unclear which prepositions to use. Maybe you prefer off. Anyway, so this is the definition. Maybe an example. Yeah, at first sight it seems to be unlikely to find such a thing. Even for one matrix, well, that's kind of hard, and you have to use some algorithms to find eigenvectors. And now we want to find vectors which are eigenvectors for all the elements of our Lie algebra, so for all these infinitely many matrices. But in fact, there are examples where this exists. So let's start with the following one. L is the Lie algebra of strictly upper triangular matrices. So n is some arbitrary number, so we fix n by n matrices, which are 0 on the diagonal and below, and may have arbitrary values above the main diagonal. So I think we already saw maybe several times that this is indeed a Lie subalgebra of GLN. And I claim that En, so the last standard basis vector, is such a weight vector. Well, let's just calculate it. If X is an element of the Lie algebra, well, so just do the matrix vector multiplication, and we see that this vanishes, because here the only non-zero component is the last one, and if I do the multiplication, there are only zeros in the last row. So this is 0, and this is yeah, 0 times, I write it as 0 times En. So this is in fact a simultaneous eigenvector, and the eigenvalue is always 0. Here the eigenvector is independent of, the eigenvalue, sorry, is independent of the matrix. And in general, the eigenvector may depend on the matrix, but here it's not. Anyway, so this is the first example. So En is a weight vector. Yeah.
I think in your 3.1 definition that it's important that the lambda depends on X.
Yeah. Darren. Right.
Yeah.
Yeah, just so I'll.
You just said in general it depends on X.
Yeah, I want to. Yeah. Okay, let me not correct it here or restate it here, but I want to write it as a remark on the next blackboard. Maybe do the second example, so there it becomes apparent that in general the eigenvalue will depend on the matrix. So it's a similar thing, but here we don't take the strictly upper triangular matrices, but all the triangular matrices. So we allow arbitrary components on the diagonal. And again, I claim that En, the last standard basis vector, is a weight vector. So let's just check it. So I've taken arbitrary matrix A11, A12, and so on, ANN, A1n. They're all zeros. I multiply this with a En vector. No. So this is by the same, just do the matrix vector multiplication and I get 0 or everywhere there's zeros except ANN in the last component. So this is ANN EN. So here this depends on X. Because it's the component in the lower right corner of X. So and in fact, it's usually a good idea to restate this definition as follows. So that the dependence on the matrix X becomes apparent. So if I have a non-zero vector in the vector space, then this is a weight vector. If and only if, well, for each lambda I want to find such an eigenvector, so I can write this as a function. There is a function lambda from the Lie algebra to the field such that the function associates with every matrix the corresponding eigenvector. For all x in L, x v equals lambda of x v. So this is just, I guess, your remark.
I have a question about your example B.
Yeah.
I must be missing something. I thought multiplying by en would pick out the last column or something. Do you mean to choose a diagonal x?
Ah, maybe I do. Right.
Maybe you meant a diagonal.
I guess so. Or this. What else have we got? And here it's also the same thing, right? I got it all wrong. Okay, good. So maybe the better thing is to choose EU1, so I have to change less things. This your remark applies already here. Huh? Right, sorry. And here also I choose E1. Right, good. Yeah, or of course, if I take just diagonal matrices, then En would also be a weight vector, or in fact any of the standard basis vectors. Good. So we think of lambda as a function on the Lie algebra. So in the example B above, lambda is the projection on the first component. So maybe I write this as epsilon 1, 1. This is by definition the projection on the 1, 1 component of a matrix. So let's investigate these kind of functions which occur here more closely. Lemma and also a definition. Such a map lambda is called a weight. So for the given let's just call it a weight. L, if there is such a weight vector. So we find a simultaneous eigenvector of L such that lambda gives us the eigenvalues. So for each element of the Lie algebra, xv equals lambda of x v. So the weight vectors are the simultaneous eigenvectors, and the weights are the simultaneous eigenvalues of these vectors. Yeah. So this was the definition part, and the lemma part is the following. Lambda is a weight then we have the two properties that lambda is a linear function. Now that means, in other words, it's an element of the dual vector space of L. So by L star, I mean the set of all linear maps from L to F. And the second property, given lambda, I can consider the space V lambda of all simultaneous eigenvectors, the eigenvalues of which are given by this lambda. So this is the set of all elements in the vector space such that any matrix acts by multiplication with lambda of x. So this is the set of all weight vectors of weight lambda, and also the zero vector. Yeah? So the way I made the definition, zero is not an eigenvector, so zero is not itself a weight vector, but it's also contained in this set V lambda. And why do I include it here? Because then I can show that this is a vector subspace. V the weight space. So this is the analogon of an eigenspace. If you just consider one linear map, the weight space associated with lambda. Okay. So we have eigenvectors, eigenvalues, and eigenspaces, and similarly here we generalize this theory, so we have weight vectors, weights, and weight spaces. Yeah, proof. Yeah, it's not really difficult, but just I think the most difficulty of this weight business comes from the fact that everything is a bit confusing at first sight. So let's just do the simple computations to get used to the notation and these notions. So claim lambda is a linear function. So I have to, the first thing is to show that it's additive. So that's lambda, we fix lambda a weight, and now we fix a corresponding weight vector. Lambda. So what we want to show is for all x, y elements of the Lie algebra, lambda of x plus y is lambda of x plus lambda of y. And this is the first part for the linearity of lambda. So how do we do it? Well, so this is a lambda of x plus y is just a scalar element of f, and we multiply it with this chosen weight vector. There is one, as as we suppose lambda to be a weight. By definition, if we scale the vector v by lambda of x plus y, this is just the operation of x plus y on v by matrix multiplication. So this is the same thing as considering the matrix x plus y and the matrix vector product x plus y times v. So now we just do matrix calculus. So this is xv plus yv. But now we can use again the property of lambda being a weight. So and v being a weight vector. So multiplication by the matrix x is just scaling by lambda of x. So this is lambda of x times v. Similarly, multiplication of v by y is just scaling by lambda of y, by the scalar lambda of y. So now I can just write this as lambda of x plus lambda of y times v. And as I supposed v to be non-zero, from this it follows that the scalars coincide. Okay. We have a non-zero vector. Okay, and the next step is to show that it's compatible with scaling, but this is similar, so I won't demonstrate this here. So scaling similar. So we've seen that any such weight is a linear function. Okay, next step is to consider the weight space, which is defined just as a set of simultaneous eigenvectors. So we have to show that this is actually a vector subspace. And as before, I'll just show part of the calculation. Namely, say that it's closed under sum. So I fix v and w and v lambda. So v and w are both either weight vectors or 0. So they fulfill this property that any matrix in L acts on these vectors just by scaling with lambda of x. So I have to show that v plus w is also contained in v lambda. So I have to show that v plus w fulfills this property. So I have to fix any element of the Lie algebra and have to compute x times v plus w. Well, but this is, so now it's just simple matrix arithmetic. So as v is contained in v lambda, x acts on v just by scaling with lambda of x. W is contained in v lambda. X acts on w just by scaling with lambda of x. Yeah. So this is lambda of x times v plus w. So I've shown that v plus w fulfills this property defining elements of v lambda. So v plus w in v lambda. And again, the rest is similar. So we would have to show that v lambda is closed under scaling, and also that it's non-empty. So, but this is clear because the zero vector is always contained. So I think everything is not really difficult, but might be a bit confusing, but it should be okay. Blah, 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 blah. Aha. Okay, so far we considered sub-Lie algebras of GLN, and now you consider an arbitrary Lie algebra. So that means we don't suppose anymore that it's a subalgebra of some GLV. And as I said, the idea of representation theory is somehow that the subalgebras of GLV are the simple ones, the ones you would want to study, or you can easily study maybe. So this gives rise to the following definition. So again, now I take a vector space V, just some finite dimensional vector space. And then I can define what a representation is of L on V. This is a homomorphism of Lie algebras. Say phi from L to GLV. And some more names. So in this case, the vector space V is called the representation space. Of phi of the representation. So I should remark that the terminology is slightly cheated. Because does this have an own number? Now, if we have such a representation, then the image I think we learned in the first lecture that this is a Lie subalgebra then of GLV. So this is one of the type of Lie algebras we studied in the first part of this lecture. So this is isomorphic to the quotient of L by the kernel of this map phi. So what actually phi is, it's an embedding of a quotient of this given Lie algebra L in some matrix Lie algebra, but not L itself. So so it doesn't really, possibly doesn't really represent L in an intuitive sense. But this is somehow to make the theory nicer, so it's just as, I don't know, just as people think about imaginary numbers, because then it's easier to talk about polynomials, and here it's the same. So actually, I think the good picture is what people want is they want to embed a given Lie algebra in some GLN, but it's to get the nice theory, it's good not really to look at actual embeddings, but also to look at embeddings of quotients. And then this is the notion you get. Yeah, example. In fact, a very fundamental example. So recall the notation I introduced in the first lecture. So instead of writing the bracket of x and y, so this is an element of Lie algebra, I just define a linear map at x from L to L, where at x is left bracket multiplication with x. So, and this operator is applied to y. So this is for at x is a linear map from L to L, which sends y to xy. Because the bracket is bilinear, it's in particular linear in the second component. So this is a linear map. That means at x is contained in GLL. So now it starts to get totally confusing. L is a Lie algebra. In particular, it's a vector space. So for the moment, we forget about the Lie algebra structure and just consider it as a vector space. So L has the role of V before here. So GLL is just the set of linear maps from this vector space into itself. As I said, for fixed x, at x is a linear map from L to L. So it's an element of GLL. It's a linear map. So add itself, now so far I considered x as a fixed element and just considered this as a function in the second argument. But if I consider add itself, this is a map which sends any element of the Lie algebra to such an operator. Namely, x is sent to at x, which is just left bracketing with x. And of course, the claim is that this is a representation. Maybe I want to conserve the definition. So it's a representation. So I have to show that it fulfills this definition. So and also here the definition of this this representation has its own name because it's particularly important. So this is called the adjoint representation. But let's prove it. Now we have to prove that this map phi, which is so this map ad here, is a homomorphism of Lie algebras. So the first property is to show that ad is a linear map. Well, again, the bracket is by definition of a Lie algebra bilinear. So far we used linearity in the right argument, and linearity in the left argument just amounts to linearity of this map ad. So this is clear as the bracket is linear on the left. Linear in first argument. Yeah, the second property we have to show is that it's compatible with the Lie brackets. So we have to show for any xy elements of the Lie algebra, at x, at y is the same as at of x, y, right? Yeah, all these are linear operators. So this is an equation in GLL. So all these, both sides of the equation are operators on the Lie algebra. So we check them by evaluating them on a test vector. So let Z be an element of the Lie algebra. So Z has the role of a test function, a test vector. So we prove this equation by evaluating it. So here, this is the bracket in GLL. So this is the bracket in a matrix Lie algebra. So this is just first argument times second argument minus second argument times first argument. So let's just write it down. At x at y z minus at y at x z, right? So maybe we should switch to a bracket notation back, because this is now a computation in the Lie algebra. So at x is applied to at y z. So this is just y z minus at y is applied to at x z. So this is just the bracket x z. So now I changed the second at into the bracket notation. So that's x, y, z minus y, x, z So of course the only thing, the definition of a Lie algebra we haven't used yet is the Jacobi identity. So this is what we want to use now. So we want to have two of the three summons in the Jacobi identity and say that they are equal to minus the third one. So here's the cyclic order is x, y, z. Here it's x, z, y. So they occur in different cyclic orders here, the variables, so we can't apply the Jacobi identity. But also there's the minus sign, which is annoying. So let's just switch these two variables, and then by the property of being alternating, the minus sign vanishes, and we get x, y, z plus y, zx. First I use that is alternating, and then that's linear in the second argument to get the minus 1 out of the exterior bracket and to cancel with this minus. Now I can use the Jacobi identity. The Jacobi identity says if I have nested bracket expressions of this type, and I have three summons where the variables occur in cyclic permutations, then this will amount to 0. So you have x, y, z, x, y, z. So the missing one is, here x is in the last position and in the first, so the missing one is x, y, z. And of course I get a minus here because I put it on the other side of the Jacobi identity. So slowly we should also look at what do we want actually. We want to show. So let's start from the end and try to match it. We want to get this operator at xy applied to our test vector z. So let's just apply the definition. That means this matrix xy is just bracketed with z. And now we see by the property of the bracket to be alternating, this is exactly the same. So I switched the arguments of the exterior bracket here, and this amounts to a change in the sign. Right. So we have proven this identity of operators by applying the operators to this test vector and using essentially the Jacobi identity. So this proves that this ADMAP is actually gives a representation of L on L. Important example. Yeah, another example which is not as fancy but occurs often also. If L happens to be already a subalgebra of some matrix, GLV algebra. We can take by phi just the inclusion of L into GLV. It's a subvector space, so there is a natural map which just sends any matrix to itself. So this defines a representation of L on V, and there are several names for this around. In the book it's called the natural representation. Also, names I heard in other places are vector representation or the defining representation. Anyway, so this is a more basic example, but still another example. So what I want to do next is to, no, let's do the other thing. Some notation. So in many discussions, we start with a fixed representation. And then it's somehow annoying always to have this map phi around, because it doesn't really enter the discussion. So if we study a fixed representation phi from a Lie algebra on some vector space V, it's often well, I don't know whether it's a good idea, but it's a usual idea to omit phi from the notation. So we define x v phi of x v for all x in L v. So just use the multiplication notation, an element of the Lie algebra times a vector. And what I mean by this is, well, take the image of x under this map phi. So this is a matrix. So this is a operator on the vector space V, and then apply this operator to V. But we omit the V. So if we use this notation, what's the structure defining a representation? Given a representation, we have, of course, the Lie algebra. Then we have the vector space V in which the Lie algebra acts, so the representation space. And here the structure, in our definition, the structure is given by a homomorphism phi from L to GLV. And if we omit phi from the notation, maybe one could also try to omit it from the definition. And one can view the structure defining a representation of L on V as a product, as a bilinear map. Just this product here. So this takes an element of the Lie algebra, and it takes a vector, and it produces a new vector. So the new vector xv is by definition just what I wrote here, phi of x applied to v. And yeah, then the property is put this on the as an exercise to show that it actually corresponds to the definition of a representation in terms of phi, in terms of this map of this homomorphism of Lie algebras, such that such a bilinear map must fulfill so if I take a commutator, this is again an element of x, and then I form this bilinear product, and this should be the same thing as x, apply this to a vector, x, y, v. So this is the same thing as forming the product yv. This gives another vector. And then I form the product x, this new vector, minus y xv. And people who use this notation often call representations modules. So in this notation, say V is an L module. If so saying V is an L module means fix a representation of L on V and omit phi, the structure map, from the notation. Okay, so I leave it as an exercise. I think it's the last exercise on this new sheet to show that these are actually equivalent concepts. And yeah, so the last thing for today is to pull back our notions of weight spaces, weight vectors, and weights to arbitrary representations of Lie algebras. So I don't use this short module notation, but just usual notation for a representation of L on V. And yeah, recall the image of phi is then a sub Lie algebra of GLV. So the image of phi is of the kind of Lie algebras we studied in the first part of the lecture. So if I have a linear form lambda on this Lie algebra, this can be a weight of this Lie algebra. Again, so this means that these matrices act on V by scaling some simultaneous eigenvector. Then I define lambda tilde to be just lambda composed with phi. So this is then a linear form on L, on the Lie algebra we represent. And this is also called a weight. So this is a weight of L on V. Thanks, no star, right, that's true. Right. Yeah. Then, yeah, and the other things similarly. If V lambda is also denoted V lambda tilde in this case. So lambda is a linear form on the image. So we have a weight space, so the set of all vectors which are simultaneous eigenvectors with these eigenvalues lambda. So if we have such a representation, then we also say this is the weight space of weight lambda tilde for L. Is there 5 minutes? Oh, 3 minutes. Yeah, let's do just an example, because this is, again, can be confusing. A very simple thing. L is just the one-dimensional real vector space, and the Lie bracket is 0. So this is an abelian Lie algebra, one-dimensional real abelian Lie algebra. And we consider the following representation, phi. So this is a representation on R2, which sends an element x of the Lie algebra, so a real number, to the matrix x 2x, diagonal matrix x 2x, and 0 on the off-diagonal components. So one sees as these commute, diagonal matrices commute, so this is actually a representation of this Lie algebra. And let's compute the weights. So what's the image of phi? That's the set of all vectors of all matrices x 2x. Where x is any real number. And did I denote this? I think epsilon 1, 1 should be the projection on the 1, component of a matrix. So I claim, I hope now I got it right, that E1 is a weight vector. Of weight epsilon 1. Well, why? How do I verify it? Just I take such an element of the image and apply it to the vector, and this gives x times 1, 0. So x is just the 1, 1 component of x 0, 0, 2x times the vector. Huh? So this is the property this has to fulfill. Now we do the pull back by phi, denote by epsilon the identity map on R. So this is a linear form on R. So by definition, epsilon 1 is a weight vector of weight epsilon.